You hear whispers about comets, ice chunks left over from when the solar system formed. You see them on late-night astronomy posts, trailing bright tails behind them as they zip past the sun. But nobody tells you about the visitor that arrived in 2025, carrying water from a star system we will never reach. 3I Atlas, the third interstellar comet ever recorded. A messenger from the ancient Milky Way that is releasing water where it should not be releasing anything at all. 40 kilograms per second, like a fire hose running at full blast. At a distance, where most comets stay silent and frozen, how does that happen? Why does an object from another planetary system bleed water almost 3 times farther from the sun than Earth, while solar system comets remain quiet? And what does that tell us about the chemistry of worlds formed around stars we cannot see? In numbers that force astronomers to recalculate what they thought they knew about how distant planetary systems deliver the building blocks of life. This is not speculation. This is documented science, published in August and September of 2025. This is a story about an ancient fragment of ice and rock that traveled for billions of years across interstellar space, arrived at our solar neighborhood, and immediately started doing things comets are not supposed to do. On July 1st, 2025, the Atlas Survey Telescope in Rio Hurtado, Chile, flagged an object moving through the southern sky. Early observations showed something strange. The trajectory was hyperbolic, too fast, moving at 130,000 miles per hour. That speed means it did not originate in our solar system. It came from outside, from interstellar space. Within days, observatories worldwide confirmed the object followed an unbound path around the sun. It would swing through once and leave forever. No return trip, no closed orbit. The Minor Planet Center received reports. Pre-discovery images surfaced from archive data going back to June 14, 2025. 3 different Atlas telescopes had seen it. Caltech's Zwicky Transient Facility at Palomar Observatory had captured it in their scans. The Vera Rubin Observatory had imaged it during science validation observations from June 21st to July 3rd. NASA's Transiting Exoplanet Survey Satellite had photographed it from May 7th to June 3rd, when it was roughly 6.4 astronomical units from the sun, already bright. Already active, far beyond where water should be driving cometary behavior. Tumbling, cigar-shaped or pancake-shaped, depending on who you asked. Borisov emitted abundant carbon monoxide and looked like a typical solar system comet in almost every way. 3I Atlas? Water. Lots of water. At a distance that breaks the rules. If you value documented interstellar comet chemistry and ultraviolet spectroscopy like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the Astrophysical Journal letters where Dennis Bodwitz from Auburn University and Zexi Xing published their hydroxyl detection paper in September 2025, with DOI 10.847/2-041-82, 13/A08 Abe, and from the NASA Goddard preprint server, where Martin Cordner led the JWST NIR spec team that published the carbon dioxide coma analysis on August 25th, 2025, archived as AORC Archive 2508.18209. These are not press release summaries. These are peer-reviewed detection papers with raw spectral data and production rate calculations. Now back to the information. Matthew Hopkins from Oxford University presented findings at the Royal Astronomical Society's National Astronomy Meeting in Durham on July 11th, 2025. His team traced the comet's path backward through the Milky Way. The vertical velocity component was high, 18.5 kilometers per second upward through the galactic plane. The radial component showed it moving away from the galactic center at 51 kilometers per second relative to the sun. That trajectory suggests origin from the Milky Way's thick disk, a population of ancient stars orbiting above and below the thin plane where the sun lives, stars with lower metallicity, less heavy elements. Hopkins ran statistical models based on typical ages of thick disk stars, 68% confidence interval, 7.6 to 14 billion years old, possibly older than the solar system by 3 billion years. Independent analysis by Astor Taylor and Daryl Seligman arrived at 3 to 11 billion years. Broad agreement, 3I Atlas could be the oldest comet ever seen. Chemistry is another, and the chemistry started showing its strangeness almost immediately. Ultraviolet light from water molecules breaking apart in space gets absorbed by our atmosphere before it reaches ground telescopes. SWIFT sees what ground instruments miss. On July 31st and August 1st, 2025, SWIFT's ultraviolet optical telescope pointed at 3I Atlas. The comet was at 3.51 astronomical units from the sun on the first visit, 2.9 astronomical units on the second visit in mid-August. Dennis Bodowitz, professor of physics at Auburn University, led the observation campaign. His team stacked dozens of short exposures. 42 minutes of visible light integration time, 2.3 hours of ultraviolet. The signal was faint, but it was there. Hydroxyl emission near 3,085 angstroms, the ultraviolet signature of water molecules dissociating under sunlight. Water molecules released from the comet. Sunlight breaks them apart. Hydroxyl radicals scatter ultraviolet light at a specific wavelength. Detect the hydroxyl, calculate the water production rate. First visit yielded a marginal detection. 0.74 plus or minus 0.5 times 10 to the 27th molecules per second. Second visit showed clear detection. 1.3, 6 plus or minus 0.35 times 10 to the 27th molecules per second, 40 kilograms per second. The rate you get from a fire hose running at full blast. Only about 1/9 the intensity compared to Earth's orbit. Surface ice should not sublimate efficiently. Direct nucleus sublimation should not drive water production at those rates. Yet the hydroxyl signal was strong, growing between late July and mid-August. Something else was powering the outflow. Hubble Space Telescope measurements placed an upper limit on the nucleus radius at 2.8 kilometers. That gives a maximum surface area. If 19 square kilometers are active, that means over 20% of the surface is sublimating. Most solar system comets show active fractions of a few percent. 5% is considered high, 20% is extraordinary. For an interstellar object that may have been drifting through space for billions of years, exposed ice covering 1/5 of the surface does not make sense unless something unusual is happening. Zexi Xing, postdoctoral researcher at Auburn and lead author on the water detection paper, pointed to near-infrared observations from early July. Gemini South and NASA Infrared Telescope Facility detected water ice in the coma on July 5th and July 14th, 2025. Not just vapor. Ice grains, solid particles floating in the cloud around the nucleus. Analysis of absorption features suggested grain sizes smaller than 1 micrometer. Submicron ice crystals, possibly amorphous rather than crystalline structure. These grains were not sitting on the nucleus surface. They were ejected, lofted into space by other volatiles. Carbon dioxide and carbon monoxide sublime more easily than water. They outgas even at large distances. As they vent from the nucleus, they carry dust and ice grains with them. Once in space, these tiny grains have enormous surface area relative to their mass. Faint sunlight heats them. The ice sublimates directly from the grain surfaces. Water vapor spreads through the coma without ever touching the nucleus, an extended source. Sublimation, happening thousands of kilometers from the comet's core. Ice grains carried outward by carbon dioxide and carbon monoxide jets, heating under solar radiation, releasing water in a diffuse cloud. Only a handful of distant comets have shown this behavior. Comet C, 1980. E1 Bowel displayed hydroxyl emission at 5.3 astronomical units in 1984. The inferred active area was implausibly large, unless icy grains contributed. Comet C, 2009 P1. Garrett showed elevated water production beyond 3.4 astronomical units observed by Swift and Soho Swan. Extended sources. Non-monotonic evolution, suggesting transient grain-driven activity. The detection of hydroxyl emission happened before any cyanogen emission. That order is unusual. Cyanogen is bright, easy to detect, often seen first in distant cometary activity, yet hydroxyl appeared first. That suggests large, ice-rich grains present in the coma early, shedding water directly. Near-infrared observations from July support the idea. If correct, the water signal comes not just from nucleus sublimation, but from material lofted into the coma. 3. I-Atlas is genuinely water-rich with low abundances of carbon monoxide, carbon dioxide, and cyanogen. That would point toward formation in the outer regions of an old low metallicity planetary system. Large amounts of water ice, but fewer heavier volatiles. Second scenario. It is rich in hypervolatiles like carbon monoxide and carbon dioxide. The water we see now is driven off by grain sublimation. As it approaches perihelion and sunlight penetrates deeper, the outgassing profile could shift toward those more volatile species. Similar to what happened with 2I Borisov. Webb's near-infrared spectrograph captured spectral images spanning 0.6 to 5.3 micrometers. Martin Cordner from NASA Goddard Space Flight Center led the analysis team. The spectrum revealed a carbon dioxide-dominated coma, enhanced outgassing in the sunward direction. Presence of water, carbon monoxide, carbonyl sulfide, water ice, and dust. The carbon dioxide to water mixing ratio hit 7.6 plus or minus 0.3. Updated value from later analysis settled at 8.0 plus or minus 1.0, 8 to 1. Among the highest ever observed in a comet. The paper notes it sits 4.5 sigma above the trend for long period and Jupiter family comets as a function of heliocentric distance, excluding the outlier comet C 2016 R2, which also showed extreme carbon dioxide enrichment. 6.1 sigma above the typical value in one version of the analysis. Carbon monoxide at 14 plus or minus 0.9 kilograms per second. Carbonyl sulfide at 0.4, 3 plus or minus 0.09 kilograms per second. Carbon dioxide dominates, 8 times more carbon dioxide than water. That inverts the normal comet chemistry pattern. Most comets show water as the primary volatile. Carbon dioxide exists, but in smaller amounts. 3, I-Atlas flips the script. The bulk chemistry is what stands out. Normal isotopes. Extreme volatile dominance. That suggests the environment of formation set this comet apart. Not the raw materials, but the conditions under which those materials assembled. 3. I-Atlas formed close to the carbon dioxide frost line in its parent protoplanetary disk. Carbon dioxide ice abundant, water ice less so. The frost line marks the distance from a star where specific volatiles condense into solid ice. Move the frost line inward or outward depending on the star's luminosity and the disk's temperature profile. A comet forming just beyond the carbon dioxide frost line would lock in high carbon dioxide to water ratios. 2. The nucleus developed a thick insulating crust over billions of years. Heat penetration is inhibited. Water sublimation is suppressed relative to carbon dioxide and carbon monoxide, which sublime at lower temperatures and can escape more easily. Either way, the result is the same. A gas coma, unlike anything in the solar system. SphereX observed 3I Atlas from August 7th to August 15th, 2025. Multispectral observations at distances between 3.3 and 3.1 astronomical units. The coma, clearly resolved, is rich in carbon dioxide and water. No tails or jets visible at that time. The coma measured out to a radius of 23,000 kilometers. High production rates. The comet itself, according to Hubble measurements, has a nucleus radius around 2.8 kilometers. Diameter somewhere between 0.32 and 5.6 kilometers. Most likely, estimate less than 1 kilometer across. Small nucleus, big coma, driven by volatiles more active than water. Cyanide emission first detected on August 14th. Throughout July to August, VLT observed a rapid and steady increase in the concentration of nickel and cyanide in the coma. The comet's activity increased as it approached the Sun from 4.4 to 2.85 astronomical units. Estimated emission rates by August 21st, 4.6 plus or minus 0.7 grams of nickel per second, 17.6 plus or minus 2 grams of cyanide per second. Atomic nickel is not unusual in comets, seen in various solar system comets including 2I Borisov. But no iron vapor was detected in 3I Atlas. That is unusual because nickel and iron typically appear in roughly equal amounts when outgassing from comets. The absence of iron while nickel is present remains unexplained. If you value documented volatile chemistry and spectroscopic analysis like this, subscribe. Comment from which city you're hearing this from. This script is researched and factual, using sources from RCIV 2 508.18209 published August 25th, 2025, where Coordinaire and 13 co-authors detail the JWST NIRSpec integrated field unit spectroscopy, showing the carbon dioxide dominated coma with spatial mapping of gas distributions and continuum subtracted emission bands, and from the Astrophysical Journal Letters, where Xing, Bodowitz, Oset, and Noonan published the swift UVOT hydroxyl detection, with water production rate modeling assuming reddening values between 29 and 38% and calculating active surface areas assuming equilibrium sublimation temperatures. These are not summarized findings. These are raw observational papers with error bars, spatial apertures, and modeled fluorescence efficiencies. Now back to the information. 3. I-Atlas reached closest approach to Mars on October 3, 2025. Distance 0.19 astronomical units, about 17 million miles. ESA's ExoMars Trace gas orbiter captured images on October 3rd. The comet appeared as a fuzzy white dot, the coma visible. Nucleus too distant to resolve. The task was challenging. The comet was 100,000 times fainter than the Martian surface the orbiter normally observes. The observation confirmed the comet's activity. The coma extended over 1,000 kilometers wide at that distance. ESA's Mars Express also attempted observations. The Jupiter Icy Moons Explorer, JUICE, prepared to observe the comet after its closest approach to the Sun in late October. Distance 1.36 astronomical units from the Sun, just inside the orbit of Mars. between Earth and Mars. The comet passed through solar conjunction on October 21st when it moved behind the Sun relative to Earth. GOES 19. Weather satellite observed it during conjunction. After perihelion 3, Atlas will speed away. It will pass Jupiter in March 2026, then exit the solar system forever. No return. Its hyperbolic trajectory ensures it will escape the Sun's gravity and return to interstellar space, probably never encountering another star system for millions or billions of years. Most comets begin showing activity no closer than 5 astronomical units. 3, Atlas started early. That suggests volatile ices other than water driving the initial outgassing. Carbon dioxide, carbon monoxide, ices that sublimate at lower temperatures and greater distances. TESS was not designed to study fast-moving comets. Researchers used image stacking techniques to reveal the object. Pre-discovery data extended the observation window by almost 2 months. The comet was 277 million miles from Earth. Hubble revealed a teardrop-shaped cocoon of dust coming off the nucleus. Because Hubble tracked the moving comet, background stars appeared as streaks in the exposure. Hubble observations as of August 20th provided updated estimates on nucleus size. Upper limit on diameter, 3.5 miles or 5.6 kilometers. Could be as small as 1,444 feet or 440 meters across. Continuing observations allowed astronomers to refine size estimates. The nucleus is irregularly shaped like other comets. That should cause periodic variations in brightness as it rotates toward the comet's direction of motion, not away from the Sun like a typical tail. This sun-facing feature is not a tail. It is a dust plume emitted from the heated, sunlit surface of the nucleus. Ice sublimation occurs faster on the sunlit side, ejects more dust. The sun-facing elongation resembles other distant comets like C 2014, UN 271, Bernardinelli-Bernstein, known to preferentially eject dust from the sunlit side. By late August, the coma no longer appeared elongated toward the Sun. The comet had developed an antisolar tail. However, the sun-facing plume remained present. Telescope images from August 26th showed the inner coma within 5 arcseconds from the nucleus, appeared fan-shaped and slightly brighter on the sun-facing side. Polarization measurements of 3I Atlas appear similar to trans-Neptunian objects. Suggests the coma is made of a mixture of icy and dark material. Spectral slopes in the optical range measured between 5 and 15% per thousand angstroms in most studies. Some higher values, up to 22% per thousand angstroms, reported at shorter blue wavelengths. The reflected continuum remained largely featureless, no obvious ice absorption features in the 0.5 to 2.5 micrometer range in many observations. Indicates that grains in the coma were dominated by refractory organics and silicates, as in typical comets. Water ice features appeared in near-infrared but were subtle. Analysis of absorption features in JWST's spectrum suggests water ice in the coma consists of fine grains smaller than 1 micrometer in size. The water ice is likely amorphous, although crystalline water ice cannot be ruled out. Amorphous ice forms when water vapor freezes rapidly without time to organize into crystal structure. Crystalline ice has ordered structure. Amorphous ice transitions to crystalline ice when heated above a certain temperature. The fact that 3I Atlas shows possible amorphous ice at 3.32 astronomical units suggests the grains formed recently or remained cold enough to avoid crystallization. The water ice grains were most likely ejected from the nucleus by outgassing of volatile substances such as carbon dioxide and carbon monoxide, rather than water ice sublimation. That mechanism explains the extended source. Carbon dioxide vents from the nucleus, carries ice grains with it. Grains heat in space. Water sublimates from grain surfaces. Hydroxyl emission spreads through the coma. The Swift Observatory detects the hydroxyl signal thousands of kilometers from the nucleus. 2 main hypotheses. 1. The comet has a carbon dioxide-rich nucleus. It may have been exposed to high amounts of radiation in its original star system or during its journey through interstellar space. Radiation processing can alter surface chemistry. Alternatively, it may have formed close to the carbon dioxide frost line in its parent star's protoplanetary disk. That would naturally lock in high carbon dioxide content. 2. 3. Atlas contains more water than suggested by JWST observations, but has an unusually thick, insulating crust, hiding water ice underneath. The crust suppresses water sublimation while allowing carbon dioxide and carbon monoxide to escape. Further observations by JWST, especially when the comet becomes more active near and after perihelion, will help determine which scenario is more likely. Yang Guo and collaborators published a study in September 2025 tracing the comet's path through nearby stars over the past 10 million years. 3I Atlas may have passed within 1 parsec, 3.3 light years, of 25 known stars during that time. Only one nearby star, measuring about 70% the mass of the Sun, appears to have impacted the comet's trajectory at all. The impact was negligible. That suggests 3I Atlas has been traveling for billions of years without significant gravitational perturbations from close stellar encounters. Its origin belongs to the border of the thin disk or the thick disk, a very old object. If it originated from around an old star in the thick disk, that implies the comet formed in a low metallicity environment. Stars in the thick disk have fewer heavy elements than stars in the thin disk, like the Sun. Planetary systems forming around those stars would have different chemical inventories: less carbon, nitrogen, oxygen in heavy molecular form, more primordial hydrogen and helium. Comets forming in such environments could have different volatile ratios. The vertical velocity component of 18.5 kilometers per second is quite high compared to nearby stars and other interstellar objects. That means 3I Atlas follows a tilted orbit around the Milky Way, belongs to either the thin disk or thick disk populations. The thick disk consists of older stars, whose compositions have lower levels of heavy elements than the Sun. Statistical analysis by Hopkins and collaborators estimated with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old based on typical ages of stars in the thick disk. The Milky Way's thin disk formed more recently. It contains the vast majority of the galaxy's stars and star-forming gases. Most stars are rich in elements heavier than hydrogen and helium, picked up from older generations of stars that lived and died before them. The broader thick disk, wrapped around the borders of the thin disk, has long ceased its star formation, contains the galaxy's oldest stars, lower metallicity. If 3I Atlas came from the thick disk, it represents material from the early Milky Way, a time capsule. Frozen chemistry from a planetary system that formed when the galaxy was young. Its speed has likely undergone changes during its journey through interstellar space via gravity assists from close encounters with stars and nebulae. Pinpointing the exact star system of origin is impossible, but the galactic population it belongs to is identifiable. Thick disk, old. Low metallicity, high probability of being older than the solar system. Water exists in other planetary systems. Comets from other stars carry water. The complex ice structures indicated by extended water sources preserve information about formation conditions in distant stellar environments billions of years ago. Each interstellar comet discovered so far has revealed a different side of planetary chemistry beyond our Sun. Oumuamua was dry, no detectable outgassing, tumbling, accelerating in ways that suggested outgassing or something else. Borisov was rich in carbon monoxide, showed typical cometary behavior in most respects: coma, tail, dust. 3I Atlas is giving up water at a distance where it should not, dominated by carbon dioxide, possibly ancient. Each one rewrites what we thought we knew about how planets and comets form around stars. When astronomers detect water, or even its faint ultraviolet echo hydroxyl from an interstellar comet, they are reading a note from another planetary system, a chemical message. Dennis Badowitz phrased it that way in the press release. The ingredients for life's chemistry are not unique to our own solar system. That statement is supported by direct observation. Hydroxyl emission at 3,085 angstroms, water production rate 40 kilograms per second, at 2.9 astronomical units, documented, measured, peer-reviewed. Achieves ultraviolet sensitivity equivalent to a 4-meter ground telescope, rapid targeting capability. Observed. 3I Atlas within weeks of discovery, before it grew too faint or too close to the Sun for effective observation, stacked dozens of short 3-minute exposures. Reached integration times of 42 minutes in visible light and 2.3 hours in ultraviolet. The faint glow of hydroxyl became visible. First marginal detection on July 31st, clear detection on August 18th to 20th, water confirmed, from an interstellar visitor. First time hydroxyl gas detected from an object originating outside our solar system. Seen in only a handful of cases: Comet Bowel, Comet Garrod. Now 3I Atlas. The processes governing this behavior are not fully mapped. Grain composition, volatile distribution, ejection mechanisms, heating rates, sublimation thresholds, all variables, all uncertain. What is known is that 3I Atlas shows the signature: hydroxyl emission before cyanogen emission, large ice-rich grains in the coma early, water release from extended sources rather than simple nucleus sublimation. That pattern is unusual. Reflects differences in grain-driven outgassing or volatile inventory compared to typical comets. If 3I Atlas's coma continues to be dominated by water during and after perihelion and shows lower abundances of higher metallicity volatiles like carbon monoxide, cyanogen, and carbon dioxide, That would be the inverse of 2I Borisov. Borisov showed high carbon monoxide. 3. I Atlas shows high carbon dioxide early, but water becomes more prominent later. That trend might support the early and low metallicity formation hypothesis. The derived large size of the nucleus combined with high activity could indicate a key knowledge gap in low metallicity system, planetesimal formation, and loss mechanisms. How do large icy bodies form in environments with fewer heavy elements? How did they survive billions of years while retaining volatile ices? 3I Atlas might provide clues. Near-infrared observations from Gemini South and NASA Infrared Telescope Facility on July 5th and July 14th detected water ice in the coma, contemporaneous with early ultraviolet detections. That timing suggests grains were already present, already shedding water. The hydroxyl signal grew between late July and mid-August. Water production increased as the comet approached the Sun. From 0.74 times 10 to the 27th molecules per second on July 31st to 1.36 times 10 to the 27th molecules per second on August 18th. Nearly doubled. The comet was getting closer, sunlight was getting stronger, heating more grains, sublimating more ice, releasing more water. That requires over 8% of the surface to be active if the nucleus radius is 2.8 kilometers, larger than activity levels observed in most solar system comets. First visit on July 31st required 10.6 square kilometers. Second visit on August 18th to 20th required 7.8 square kilometers. Both numbers are high. Both suggest either a very active nucleus or a significant contribution from extended sources, probably both. The nucleus vents carbon dioxide and carbon monoxide. Those volatiles carry ice grains. The grains sublimate. Water spreads. Hydroxyl emission happens thousands of kilometers from the nucleus. The total water production reflects both nucleus activity and grain sublimation combined. The carbon dioxide to water ratio from JWST is 4.5 sigma above the trend, 6.1 sigma in one analysis. Either way, a major outlier. Only one other comet approaches that level. Comet C 2016 R2 also showed extreme carbon dioxide enrichment. But that comet was different in other respects. 3I Atlas combines high carbon dioxide, early water activity, extended sources, and interstellar origin. That combination is unique. Molecular line emission isolated by subtracting polynomial fits to adjacent continuum. Spatial coordinates relative to the brightest pixel in the continuum dust map. Gas distributions show heterogeneity, different outgassing patterns for different species. Carbon dioxide and carbon monoxide show morphology consistent with enhanced outgassing in the sunward direction. Water shows more symmetric distribution. Dust shows strong plume sunward. Heterogeneity explained by different molecular sublimation temperatures. Different nucleus release and coma acceleration mechanisms. Differing inertial and fluid dynamics for each gas and dust component. Sublimation temperature of water is higher than carbon dioxide, which is higher than carbon monoxide. That implies sublimation of carbon dioxide and carbon monoxide is more fully activated than water at 3.32 astronomical units. Observation consistent with carbon dioxide and carbon monoxide, driving early activity while water remains partially suppressed. The detection of carbonyl sulfide is tentative but significant if confirmed. Carbonyl sulfide contains sulfur, another element to track, another volatile to measure. Emission rate estimated at 0.43 plus or minus 0.09 kilograms per second. Small compared to carbon dioxide but detectable, adds to the chemical inventory. New volatiles could appear as sunlight penetrates deeper into the nucleus. The carbon dioxide crust might thin, water could dominate later observations, or carbon dioxide could remain dominant. Each scenario tells a different story about the comet's internal structure. Observations through late 2025 and early 2026 will reveal which path the comet takes. Unlike the previous two interstellar objects, 3I Atlas originated from the southern celestial hemisphere, opposite to the solar apex in the north. The solar apex is the direction of the sun's movement relative to local stars. Astronomers initially predicted more interstellar objects should come from the solar apex. Southern origin objects were thought to be harder to discover. 3I Atlas defied that prediction. Came from the south, got detected anyway. Hyperbolic trajectory confirmed, speed confirmed. Interstellar origin confirmed. The comet will pass through the inner solar system once and leave. Its perihelion at 1.36 astronomical units places it just inside Mars's orbit, close enough for good observations, far enough to remain safe. After perihelion, it will speed away. Velocity 130,000 miles per hour, 210,000 kilometers per hour, escaping the sun's gravitational influence, returning to interstellar space. material that has drifted through interstellar space for potentially billions of years. Studying it provides insights into the diversity of planetary systems and the cosmic processes that shape the building blocks of life throughout the galaxy. Water in an interstellar comet means water is common. Planetary systems beyond our sun form with water. Comets from other stars carry water. If comets delivered water to early Earth, then comets elsewhere could deliver water to other worlds. The ingredients for life are distributed, not unique to our neighborhood, a galactic phenomenon. 3. I-Atlas will not return. After it exits the solar system in 2026, it will travel through interstellar space indefinitely, may pass near other stars millions of years from now, may get captured by another planetary system billions of years from now, or may drift forever. A frozen relic from an ancient star system, carrying water and carbon dioxide and carbon monoxide through the galaxy. A bottle cast into the cosmic ocean. It washed ashore here briefly. We looked inside. We found water. The JWST spectrum includes a weak carbon-13 carbon dioxide band at 4.4 micrometers, shown in an inset panel next to the main carbon dioxide band. 3 sigma upper limit, carbon-13 to carbon-12 ratio consistent with Earth values. That constrains isotopic fractionation. Tells us the carbon isotopes are not wildly different from what we see in the solar system. The anomaly is in the bulk chemistry, not the isotopic composition, normal isotopes, extreme molecule ratios. That combination points to formation conditions, rather than fundamental differences in raw materials. 3 successive partial annular sectors, each with 0.625 arcsecond radial extent. Best fitting production rates for carbon dioxide, carbon monoxide, water, and carbonyl sulfide as a function of distance from the nucleus. Production rate curves show how gas production varies with position. Carbon dioxide production highest near nucleus, declining with distance. Water production shows extended source signature, increases in outer regions relative to carbon dioxide. Consistent with icy grains sublimating away from the nucleus. Carbon monoxide shows intermediate behavior. Carbonyl sulfide too faint to map spatially with high confidence, but present. That decoupling suggests water is not the primary driver of dust ejection. Carbon dioxide lifts the dust. Water rides along, gets released from grains afterward. The usual driver of cometary dust is water vapor. Here, carbon dioxide takes the lead, inverts the standard model. Shows how different this object is. Typical comets show carbon dioxide to water ratios well below 1 at 3 to 4 astronomical units. 3 I-Atlas sits at 8, far above the trend line, 4.5 sigma deviation. Only one outlier comet, C 2016 R2, approaches that level. But that comet was at different heliocentric distances and showed different morphology. 3 I-Atlas stands alone in combining extreme carbon dioxide enrichment with early water activity at large distances. Formed in a region of the protoplanetary disk where carbon dioxide ice was more abundant than water ice. That happens closer to the star, where temperatures allow carbon dioxide to condense but water remains in vapor phase. Or farther from the star in extremely cold regions where carbon dioxide ices dominate due to low partial pressures. Either scenario requires specific disk conditions, temperature gradients, pressure profiles, chemical abundances, all determined by the parent star's luminosity, the disk's mass, and the timing of planetesimal formation. Ultraviolet light from nearby stars during the comet's journey through the galaxy. Radiation can alter surface chemistry, strip away lighter volatiles, leave behind carbon-rich residues. If the nucleus developed a carbon dioxide-rich crust over time, that crust would dominate early outgassing. Deeper layers containing more water might remain insulated. Only later, as sunlight penetrates the crust, or as the crust erodes, would water become dominant. The presence of water, ice grains detected by near-infrared observations, and implied by Swift's extended hydroxyl emission, suggests the second mechanism is partly at work. Water is there, it is being released, but not from the nucleus surface primarily, from grains. Carried outward by carbon dioxide jets. That hybrid model combines intrinsic carbon dioxide richness with crust-inhibited water sublimation. Both factors could be true. The nucleus is carbon dioxide rich, and it has a crust. The result is extreme carbon dioxide dominance early, followed by increasing water contribution as the comet heats up and the crust thins. If carbon dioxide remains dominant, that supports the intrinsic composition hypothesis. JWST planned additional observations in late October and November. Those data will show how the comet evolves, whether water takes over, whether carbon dioxide stays in control, whether new species appear. The answer will constrain formation models. Will tell us whether 3 I-Atlas formed in a cold outer disk with lots of carbon dioxide, or in a radiation-processed environment that altered its surface over billions of years. The discovery that 3I Atlas is releasing water where it should not matters because it changes how we think about interstellar comets. We have 3 examples now, each different. Oumuamua, dry, no gas. Borisov, carbon monoxide rich, typical comet behavior. 3I Atlas. Water active at great distances, carbon dioxide dominated, possibly ancient. 3 data points, 3 different chemical profiles. That suggests enormous diversity in interstellar comet populations. Different planetary systems produce different kinds of comets, different formation environments, different volatile inventories, different surface processing histories. The galaxy is full of variety. Comets from other stars are not all alike. Each one carries a unique chemical fingerprint from its home system. We'll discover many more interstellar objects. Estimates suggest the observatory could detect dozens or even hundreds over the coming decade. Each new detection will add to the sample. We'll show more diversity, or will reveal patterns. Either outcome advances the science. If all interstellar comets show different chemistry, that tells us planetary systems vary widely. If clusters emerge, that tells us certain formation pathways are common. 3. I-Atlas is data point 3. More data points are coming. The picture will sharpen. The ESA Comet Interceptor mission is under development, designed to visit a long-period comet or interstellar object. We'll launch and wait. When a suitable target appears, the spacecraft will intercept, fly by, take close-up images, measure composition, sample the coma, maybe even land. That mission could visit an object like 3I Atlas, get in situ measurements, resolve questions that remote observation cannot answer, measure isotope ratios directly, sample the nucleus material, map the surface, see the jets up close, determine whether the crust is thick, whether the interior is water-rich, whether the carbon dioxide dominance is intrinsic or processed. Comet Interceptor will provide answers, but only if an interstellar object arrives, while the mission is active and reachable. 3, I-Atlas came too soon. The next one might be in time. Every interstellar comet so far has been a surprise. Oumuamua surprised by not outgassing. Borisov surprised by how normal it looked. 3 I-Atlas surprises by releasing water where it should not and being dominated by carbon dioxide. What will the 4th interstellar object show? Will it be water-rich, carbon monoxide-rich, ammonia-rich, methane-rich, or something else entirely? We do not know, cannot predict. Each discovery is a roll of the dice, a random sample from the galactic comet population. The galaxy contains trillions of comets. We have seen 3 from outside our system. The sample is tiny, the diversity so far is high. That suggests even more diversity awaits. Telescopes track its fading glow, measure how the chemistry changes, watch for new emissions, monitor the dust production, check whether the carbon dioxide stays dominant, see if water increases. The comet will remain observable into early 2026. Then it will fade beyond detection limits, will disappear into the darkness, will return to interstellar space, will carry its water and carbon dioxide back into the galaxy. A messenger that delivered a note and left. Says planetary systems around other stars form with the ingredients for life. Says chemistry varies. Says some comets are carbon dioxide rich. Says extended sources can drive water activity far from the sun. Says icy grains matter. Says old objects can retain volatiles for billions of years. Says the thick disk of the Milky Way contains ancient comets we can study if they pass through our neighborhood. Says ultraviolet spectroscopy works. Says space telescopes can detect faint signals. Says hydroxyl at 3085 angstroms is the signature. Says we can measure water production from interstellar visitors. Says the universe is delivering samples if we watch carefully. The teams that modeled the spectra, the teams that calculated the production rates, the teams that traced the trajectory, the teams that estimated the age, the teams that published the papers. The work happened fast. Discovery on July 1st, observations on July 31st. Paper submitted by early August, published in September. Rapid turnaround, small window. Comet moving fast, data needed quickly. Science operates under time pressure when the target is fleeting. TESS imaged it, never meant to look at comets. Image stacking revealed the object, Hubble tracked it. JWST scheduled observation, SphereX captured spectra, Mars orbiters turned their instruments, JUICE prepared, ground telescopes at Gemini, VLT, infrared facilities, Atlas stations all coordinated. Global effort, every available instrument pointed at the visitor, maximized the science return, gathered as much data as possible before the object faded. That coordination is what modern astronomy looks like. Networks, collaboration, shared data, rapid publication, open access preprints, peer review, transparency, fluorescence efficiencies, spatial apertures, integration times, all documented. That is how science works. Transparency, reproducibility. Others can check the calculations. can reanalyze the data, can test alternative models. The conclusions stand or fall based on evidence, not authority, evidence. 3. iAtlas rewrites the book on interstellar comets by adding a chapter we did not expect. Water activity at great distances, extended sources, icy grains, carbon dioxide dominance, ancient age, thick disk origin. Every new chapter changes the story. The story now says interstellar comets are diverse. Chemistry varies. Water is common, but not always dominant. Carbon dioxide can take over. Age matters. Origin matters. Surface processing matters. Formation environment matters. The message is complexity, variety, richness. The galaxy is not uniform. Comets from different stars are not identical. Each one reflects its unique history. The only way to sustain 40 kilograms per second of water production at that distance is through icy grains sublimating away from the nucleus, carried by carbon dioxide and carbon monoxide, heated by faint sunlight, releasing water in a diffuse cloud. That mechanism is rare but real. Documented in a few solar system comets, now documented in an interstellar comet. That means the physics works across different planetary systems. Extended sources are a general phenomenon, not limited to our neighborhood. Nickel and iron usually appear together. Same abundance, same behavior. 3, iAtlas shows nickel but no iron. Why? One possibility is differential vaporization. Nickel vaporizes at a slightly different temperature than iron. If the nucleus temperature is in a narrow range, nickel could sublimate while iron remains solid. Another possibility is chemical binding. If iron is locked into refractory minerals while nickel is more loosely bound, nickel could escape while iron stays behind. A third possibility is observational bias. Maybe iron is present, but the emission lines fall in wavelength regions not covered by the VLT observations, or maybe the iron lines are too faint to detect. The absence of evidence is not evidence of absence. More observations could find iron, or confirm it is genuinely missing. Either way, the nickel emission is real. 4.6 grams per second, growing steadily from July to August, tracking the increasing activity. Nickel is a tracer, shows the comet is releasing metals, breaking down minerals, outgassing not just volatiles, but also refractory elements. That is standard cometary behavior. Happens in solar system comets too. Nickel and iron vaporize when dust grains are heated, sunlight hits grains, temperature rises, metals sublimate, atoms scatter light, emission lines appear. VLT detects them, measures production rates, tracks temporal evolution, standard technique, applied here to an interstellar visitor, typically associated with organic compounds. Cyanide in comets comes from breakdown of more complex molecules. Could be hydrogen cyanide, could be cyanogen. Emission at specific wavelengths indicates which species. VLT observations on August 14th detected cyanide, later than hydroxyl. That sequence unusual but not impossible. Depends on which volatiles sublimate first. Hydroxyl appeared in late July. Cyanide appeared mid-August. Hydroxyl emission implies water. Cyanide emission implies nitrogen-bearing organics, both present, both increasing. Both tracking the comet's rising activity as it approached the sun. Moving fast. Southern sky. Orbit calculations showed hyperbolic trajectory, confirmed interstellar. Announcement went out, observatories responded, global campaign began, all within days. Speed is essential. Interstellar objects pass quickly. Observing windows are short, coordination is critical. Atlas to Minor Planet Center to observatories worldwide. Information flows fast, telescopes retarget, data pours in, papers get written, results get published. Months later, we have a detailed picture: water activity, carbon dioxide dominance, extended sources, ancient age, all from an object discovered in early July. 7 to 14 billion years old, possibly formed around a star with half the metallicity of the sun, drifted for eons, crossed interstellar space, arrived here, released water at 2.9 astronomical units when it should not, showed carbon dioxide to water ratio of 8 to 1 when comets should show the reverse, demonstrated extended sources with icy grains sublimating thousands of kilometers from the nucleus, preserved amorphous or crystalline water ice depending on grain temperature, vented nickel and cyanide and carbon monoxide and carbonyl sulfide, survived billions of years intact enough to remain active, delivered a chemical fingerprint from a planetary system formed in the early Milky Way when the galaxy was young and stars were metal poor, a message in ultraviolet light, a note written in hydroxyl and carbon dioxide, read by instruments orbiting Earth and Mars, decoded by teams at Auburn and Goddard, published in the Astrophysical Journal, Letters, and on AR Kakshkov, documented, measured, peer-reviewed, real. The water messenger, the thick disk relic, the interstellar visitor that rewrites the rules.